Okay, welcome everyone to the latest International Network on Quantum Annealing seminar. It gives me great pleasure to introduce our latest speaker, which is Callum Duncan. Callum's a postdoc working in the University of Strathclyde in Scotland. Coincidentally, the university where AQC will be hosted this summer, and I know that the website for AQC is about to go live, so look out for that. That meeting will be held in June in Glasgow. Anyway, without further ado, let's hand over to Callum, who's going to talk about the adiabatic gauge potential, control with knowledge.
Thank you, Paul. First, I want to say I don't think I'm going to really deliver fully on the title. Um, please don't be too shocked by that. It's more of kind of a bit of a manifesto, I would say, in type of talk that really what we're trying to do in Strathclyde and in Oxford in Andrew Daly's group around control problems, how we're trying to approach them and what we are trying to do. Sorry, one moment. I'm sorting a pesky thing on my screen. Cool. There we go. Okay. Sorry. So first off, the group that we have here. So of course, I work as a postdoc as part of the group of Andrew Daly, who has now moved to Oxford and is starting well, is continuing the group, I would say, down there. But we still have a sizable presence up here at Strathclyde, and for quite a few years, we're going to still be quite a sizable group. And that includes 3 other postdocs and then 8 PhD students within Andrew Daly's group. And we also work very closely with the group of Peter Curtin. And I particularly want to point out Ewan Lawrence, who the kind of final results I'll show at the end of this work is his most recent paper that he's sort of led. And also Sebastian Schmidt, because that was in collaboration with Sebastian. And also a big thanks to Yeva, who gave a previous seminar, who is now a graduate from our group and is working at Phasecraft. And a lot of this work was done in collaboration with Anatoly at Boston University. So, okay, so what's my kind of motivation for this talk? Well, adiabatic protocols are crucial for the development of quantum technologies. I hope I don't need to motivate that too much to this audience, but I mean, you can use them for state preparation, of course, is a big example. It's often adiabatic. You can, of course, do that other ways, but I think this kind of analog state preparation is probably quite a popular way of moving forwards. And then, of course, you have adiabatic quantum computing and the like. And it's also the native language quantum system that's continuous time evolution. Most methods of control of a dynamical system kind of rely on some level of classical simulation or verification, or kind of shifting the complexity onto the experimental procedure, I would say. I mean, I wouldn't say this encompasses what everybody's doing, but I think as a broad generalization, this is true of most of what we have done so far. And we being very much the royal we and the large amount of effort that has went into this. But it would be quite nice to get beyond this. I think the idea that the experimental procedure, just kind of basically iterating over the experiment to do your control, so feeding them some pulse and getting some information off that and having that all be within the experiment is not very scalable. It's not going to solve a lot of the problem. I mean, I imagine if I go down to the lab, and we're very lucky to have close collaboration with experimentalists here at Strathclyde, and I tell them, you know, they ask me, say, I want to be able to go from this state to this state. What's the best way of doing this? And I tell them, well, you need to iterate your experiment X times and then give me the information and I'll tell you what worked well. They're not going to be brutally happy with me, because whatever they're doing, they're probably having to iterate it already tons of times. So I think it's a very important part, and it'll play a role moving forward, definitely. But it shouldn't be the kind of thing that will save us. So I would say for adiabatic protocols, and there I'm really kind of meaning kind of annealing and adiabatic quantum computing, to be taken seriously by some, and by some probably they won't be ever taken seriously, but I think there's people out there that could be convinced that if we need to show progress going beyond the classical simulation barrier. And in my mind, there's kind of 2 barriers in that process. There's the dynamical, where we're actually simulating the equation of motion, see the Schrodinger equation, and then we're optimizing over that. And then there's the static as well. Like we could optimize over properties of the ground states. Say we were trying to do an annealing algorithm and we weren't wanting to follow the ground states, we could look at properties of said states to do our optimization as well. But both of these things have their limit in terms of what we can actually simulate on conventional computers before we kind of shift the problem onto the actual hardware that we want to use, the quantum hardware. So the kind of motivation for this talk is, can the adiabatic gauge potential, which I'll introduce, which was kind of brought forward by Anatolian collaborators a while ago, and is related to counter-diabatic driving and lots of stuff that has happened before, could that contribute to solving this problem? So first, let's just start from the simple adiabatic or diabatic. So the adiabatic theorem was quite nicely stated, and at least translated from German in the original paper in the 20s, that an infinitely slow change of parameters result in the transition probability between states with different quantum numbers remaining small. So essentially, if I change my Hamiltonian very slowly, then effectively I'm not changing my Hamiltonian at all at any one given time. So I should stay in the states that I have been in previously. So if I start in the ground state, I should stay in the ground state. And of course, this is true up to many caveats, especially around degeneracy and other things. But let's just start from this rather simple way of thinking about it. And it's particularly useful, something closer to my heart, where I kind of spend a lot of my time is working with ultra-cold atom experimentalists. And so adiabatic state preparation is something that they do all the time when they're simulating different problems. It's also something that plays quite well into the kind of more the topic of my PhD a few years ago now, and topological states. And here I'm not really saying anything about whether you would use these for computing or anything or whatever. Really, just if you're wanting to have an anion in your system, and then you're wanting to say, look at the particle exchange statistics, which is the interesting property about anions, you need to then adiabatically exchange or move these quasi-particle excitations. So, and because you're really caring about the phase gain, that is really, really sensitive to being adiabatic or not. And of course, there's adiabatic quantum computing, which is kind of a bit more well-known these days. And a very good example of that is the sort of maximal independent set stuff that people have been doing on the Rydberg atom arrays, but there's many, many other examples of this. Okay, so let's just quickly cover a very simple example. I hope is kind of familiar to many of you. And that's just the Landau-Zener problem. So we just have this Hamiltonian, we just have a single spin, we have a sigma x term, and we're going to drive our sigma z term linearly. And we're going to aim for basically taking rotating our spin from down to up. And of course, if we do this slowly enough, this is the spectrum as a function of lambda or time here. Then if we start in the ground state, this is the sort of red dashed line, then we will stay in the ground state. We will just sort of track it if we do that really, really slowly. But if we speed up a little bit, then we're going to get a small amount of excitations. And then if we speed up a lot more, then we end up with a lot more excitations. And we'll see that effectively, this is a very nice problem because, of course, the gap here in the system, the closest the energies get, the ground state and the excited state, because there's only two states in the problem, is of order delta. And we see that this transition from adiabatic to diabatic happens at the order of 1 over the gap. Okay. So I quite like this quote from a Hartman-Langner paper a few years ago now that discusses the kind of the natural consequence of that finding that your driving time that you need to go is inversely proportional to the minimum gap that you're going to encounter, because the minimal gap scales with the system size, of course. And in most cases, in a lot of cases, exponentially scales. It gets exponentially smaller. So the question about whether a possible quantum speedup in quantum annealing even exists is still an interesting one. So I would say to go faster, we really need to understand the diabatic terms for larger systems. Because it's not true, I think, that we always need to necessarily stay in the exact ground state, and it's not true that we need to really care about always that these energy gaps are scaling the way they're scaling, we could care about, say, a larger gap between, say, a bands of states. So, I think the adiabatic gauge potential that we're going to introduce is a good way of thinking about said things. Okay, so the adiabatic gauge potential, I think the nicest way to think about it is in terms of just some pictures first. So I have a quantum system, of course, represented by two levels. And then I am going to effectively accelerate it by some lambda. So that's basically that I have a Hamiltonian that has some lambda dependence. I'm driving some parameter in that Hamiltonian. And so I start off in the lab static frame, but I can consider the transformation that diagonalizes my Hamiltonian for all lambda. So this, of course, will depend on lambda, and it will be a unitary. And if I perform that transformation, I'll move into the co-moving frame. So now my Hamiltonian itself doesn't have any lambda dependence. It's lambda independent. But of course, my physics needs to be the same between these two reference frames. So I gain this additional terms in my equation of motion. And this is nothing more than just the same thing that goes on classically, in the sense of that if you're on a merry-go-round or spinning, you'll feel this fictitious force pushing you outward. And this is the adiabatic gauge potential. So just to put a bit more into some equations, which I hope is not too bad. So we start off with our equation of motion being the Schrodinger equation, of course, in the lab static frame. We perform our transformation, and out pops this additional term when we get out. And if you're not too into equations on slides, then I would suggest that this is where maybe you stop paying attention to this slide, because we're going to go through this just to make it absolutely clear. So we transform the Schrodinger equation by first transforming our state into the reference frame. So this is the state in the static frame. This is the state in the co-moving frame. And so I can write this out simply by expanding these things, by taking this to the Schrodinger equation. I can then apply the Hermitian conjugate of the unitary to the problem to obtain the co-moving frame Schrodinger equation. So this part, and out pops this. And this part that I've sort of now headed up. So of course, this is the transformed Hamiltonian U dagger HU. Is this A lambda is nothing more than the fact that my unitary that I'm implementing is dependent upon lambda. I get this additional term out that goes like IH bar U dagger d lambda, or the partial derivative of lambda with respect to the unitary. And what's interesting is I then transform that back into the static frame, and I find that this adiabatic gauge potential is nothing but the kind of the generators of my motion, which is quite interesting. Okay, so many of you might have, or some of you might have seen the adiabatic gauge potential before, and especially in the context of counter-diabatic driving. But we'll quickly introduce that. Counter-diabatic driving in this sense from the AGP, sorry, the adiabatic gauge potential, I'll probably do that quite a lot. I'll slip up and say AGP instead. Is we simply lift this term out. Like this is the term that describes all of our diabatic transitions. This term is diagonal. I picked the unitary that diagonalizes my Hamiltonian. So all this term here can do is the same thing as any time-independent Hamiltonian would do. It can't cause transitions between eigenstates. So all the transitions needs to be caused by this, the adiabatic gauge potential. So what if I simply take this, lift it back, and add it to my original equation of motion? Well, then when I do the transformation, I'll find that all I get is the lambda independent Hamiltonian in the co-moving frame. So I have no transitions in between eigenstates of H. Yep, so remember this is diagonal, so no transitions. And just for people that are a bit more familiar, maybe with counter-diabatic driving, you'd normally see counter-diabatic driving kind of written out in this sort of form, where the ket n here would represent the eigenstates from the time-independent Schrodinger equation for all lambda. And therefore, the adiabatic gauge potential is proportional to the derivative of my time-independent eigenstates projected back onto my eigenstates. And this is quite an important realization, because if the eigenstate is delocalized across the system, then of course this will be highly delocalized. This operator will now be highly delocalized across the system. Okay, but how do I actually go about obtaining the AGP? Because I just sort of introduced this magical unitary that chain that diagonalizes my Hamiltonian for all lambda. And of course, if I knew that, then I could solve the problem, right? I wouldn't have to do any of this because I can solve for all the eigenstates. So how do you actually go about obtaining the AGP in a scenario where you can't solve for all the eigenstates? Because also knowing that unitary without knowing all the eigenstates is difficult. We can simply look at a similar problem. We can look at the fact that, parallel transport, that the derivative of our Hamiltonian should commute with our Hamiltonian. So the adiabatic gauge potential is nothing but the connection. So I can write out the derivative of my Hamiltonian simply as this. And this is great, but it's still not that easy to just directly solve this because A lambda is an operator, it's a very complex thing. So I could just I could take a variational approach instead, which is probably the best way around it, and that's what most people do. And this is kind of called local counter driving, though if you you can of course take it to the limit where it's exact, and that's simply that I rewrite. So I consider this part, I can realize that this equation here is nothing more than solving for the minimum of the trace of this equation through some steps. They're quite a bit algebraically, well, not too involved, but it's more lines than I want to put on a slide. And then I can simply solve by minimizing this problem by taking some ansatz from my problem in terms of some coefficients that I'm going to find and some operators that I guess, or I use knowledge about the problem to inform that guess. And then I simply solve this for the coefficients in front of this to give me the AGP. And of course, in the limit where I include all possible operators that the AGP, the adiabatic gauge potential, could have support on, then this approach would give me the exact adiabatic gauge potential, and then therefore give me all diabatic transitions that are possible in my protocol. Okay, so let's consider a quick example. I can simply take the two-spin Hamiltonian, so I have a ZZ term, a local Z, just to break some degeneracies to make things simpler. I'm going to drive the X field. So basically, I'm going to drive from a down-down state to some superposition of the four possible states of the problem. And here, the one-body adiabatic gauge potential is nothing more than the sigma Y terms. Problem is the full adiabatic gauge potential would be given by the following. So I would solve for these alphas, of course, via the variational method, but I think it's more interesting to look at what happens. So these are plots of 1 minus the fidelity versus the sort of the runtime of the protocol. So here I'm driving across this transition for the state at different timescales, and out here I'd be adiabatic, and out here I'm diabatic. So this is me doing no local counter driving, so I'm not adding any of this AGP terms to the problem. And you see, at some point I just start doing badly because diabatic transitions are starting to dominate. If I add the one body local counter driving, so the gamma 1 term here, and all of a sudden I do far better, and for short timescales I can drive the system better. And then if I add two body, I of course get unit fidelity at all times. So this is really just to illustrate what this adiabatic gauge potential, the information it's encoding these diabatic transitions, and you could use that information, of course, to do control on your problem. Now, finding the AGP in more complex scenarios, say ones where maybe just taking this sort of guess that I did, these informed guesses that I did here, and then solving some simple equations where that is not going to be possible. Well, it was noticed by Peter Clays and collaborators a little while ago that the AGP is actually described by this nested commutator form. And it's quite beautiful, actually. So you can use this, and I'm not going to go into how we exactly go about that, to obtain the adiabatic gauge potential in more complex settings. And actually, we have a paper up on the archive today, which wasn't planned to be timed with this seminar, but it actually worked out quite well, where we've developed an approach at Strathclyde, a numerical approach to calculating the exact AGP in different systems. I'll present some results of that at the very end. I also wanted to point out to this other work. So there's been some great work at the start of last year on calculating similar things, or basically adiabatic gauge potential or counter-diabatic driving using Krylov space methods, which scales quite well. And I think that there's an interesting need to perhaps compare our approach to this, which we haven't yet quite got into. Okay, the adiabatic gauge potential, what is good for? So I think I kind of convinced already, perhaps, that it's good for control. So you can simply use the fact that you can find these diabatic terms that are causing your transitions. You can simply apply the negative of them essentially to your Hamiltonian to sort of counter them. Though the issue with that is doing it exactly will result in you having to apply highly non-local in most scenarios terms to your equation of motion, which is not really what experimentalists want to hear from us. So I did sketch out, of course, this approximate method, but there's no guarantee that's going to work, and especially where in cases where correlations are gonna build up over long ranges in the system, and that's kind of really where maybe we can't classically simulate. So we're going back to talk about these barriers where we can't do well with the dynamics or with even the ground state, where, say, example, tensor network methods fail, is when I have long range correlations. And I'm kind of saying, well, our method works, but only for when we don't have long range correlations. So like, are we going to win out in the end against tensor networks if we're going to actually apply it to any actual quantum hardware? We could, of course, combine knowledge of the AGP with optimal control. That's this code approach. And there's the INQA seminar from last year by Yeva on that on the 28th, which is up on YouTube, which is very good, and I highly recommend it. But this will improve the control protocol at some cost. So now we get on to the knowledge, which is kind of what I've been trying to motivate throughout this talk, that the AGP itself, the adiabatic gauge potential, describes all non-adiabatic terms. So if I go really fast, as most of the time I'm wanting to try and do, or if I wanted to try and understand why my adiabatic protocol is not working in whatever given timescale I'm doing it in, then the dominant terms are going to be these diabatic terms. They're going to be described by the adiabatic gauge potential. So can we use this information, the fact that I can solve for the adiabatic gauge potential, even potentially in scenarios where I can't solve the Hamiltonian using this variational approach? Can I use that to inform control profiles? Can I construct cost functions from the adiabatic gauge potential? Can we even implement algorithms or protocols via the diabatic terms themselves? Like, can we engineer the diabatic terms? I would say that's the more out there idea, and that's the thing that we've not really looked into yet, but something that excites me quite a lot. And also then there's big questions, which properties of the adiabatic gauge potential are best suited for this? It's not immediately clear. And also, is the complexity of solving for the adiabatic gauge potential less than that of solving any of the problems that we would set out on anyway? So that's always a big question in the mind. But regardless of all this, I mean, if I put just my pure physics hat on, non-adiabatic dynamics is, I think, very interesting and relatively unstudied, and this unlocks it. And let's turn a bug into a feature, as Andrew, my mentor, often says. So I'm going to finish off with just two quick examples. So that's one from the code paper, Counteractive Optimized Local Driving paper by Yeva, that thankfully actually she didn't cover during the seminar she gave previously. So this is still new to the INQA seminar, which is quite nice. So first, I just need to quickly outline optimal control if people are not. So what I mean by it is, of course, I have some control pulse, which is doing something to my physical system. I'm doing some measurement. Now, this could all be me simulating it or doing it in an experiment, which feeds into some optimal control protocol, which informs the pulse, and then so on and so forth. So I can construct cost functions, something that I would quite regularly do in a numerical experiment is perhaps use something like the fidelity of the state, how close to the target state am I? And the Hamiltonian is modified by the original Hamiltonian plus these optimizable parameters and their operators. And there's lots and lots of methods to do this. And the approach that I'm going to take here, or the methods we've applied here, are relatively straightforward and are optimizers that you can get out of SciPy. But the methods are fully can be extended with other things. So code, as it is, simply takes the original Hamiltonian, the optimal control part, and then also adds in this local counter driving that we were talking about before. So say I don't want to implement all these crazy non-local terms in my adiabatic gauge potential, but maybe I can implement the 1 and 2 body terms. Then what this allows is it allows for my pulse, like my optimal pulse, to kind of find the most adiabatic path considering the corrections that I'm willing to make. So we can quickly revisit the two-spin example. So this is results that I presented just before, where we have the two-spin problem and we have the one-body AGP added to the problem, and we get this sort of result. I can do optimal control, and of course I will do better in some regime. And I have to say, on this plot, we've probably quite purposely exaggerated the areas where the control is going badly. But of course it wins out in a particular regime that might be interesting for most experiments. But eventually, of course, gets killed out by diabatic terms as well. But if I do the one body code, so this is the same optimal control procedure as is done for the purple squares here, but I also apply this one body adiabatic gauge potential, the one body local counterweight driving, then I will do a lot better for these lower times for the protocol. But finally, we get to maybe the main result for what I'm trying to say during this talk about using basically control with knowledge. The thing that I think was just enough for me that allowed me to use that title. And that is, I revisit again the fact that the Schrodinger equation in the cold-moving frame is described by the diagonal Hamiltonian plus this adiabatic gauge potential. So if I minimize the adiabatic gauge potential for any given Hamiltonian, then I must minimize the diabatic transitions, right? So why not consider as a cost function instead of the fidelity or something that I have to calculate using complex routines, simply properties of the adiabatic gauge potential. So here we're going to consider the norm of the adiabatic gauge potential across the protocol path. And the important thing about this is minimizing this does not need access to the dynamics. This particular version doesn't even need access to the state. So you're talking about the optimal control procedure here would take, I don't know, fractions of a second, depending on how you're coding it up, right? No time whatsoever. I'm not having to run costly quantum dynamics. I'm not even having to diagonalize a Hamiltonian or even find a ground state at any point. So we're going to consider this on the Ising model. So ZZ interactions, local Z, we're going to allow some optimization of the Z field, the local Z field as well, through these beta parameters. And we really did just, so this is just really, really simple. It's not doing anything too complicated here. You could add all sort of bells and whistles onto this problem to make it even better. And then we're going to drive the X field again. So we're going from this kind of all down configuration to some superposition of different states in our Hilbert space. And I'm going to add the one body optimal local counterweight driving. So I'm going to add these sigma y terms. So I'm going to use some knowledge in my control protocol here already from the UGP. Sorry. And then what we're going to do is we're going to simply say, well, okay, so I've added the one body term. Now I want to minimize, say, the two body, that next order term. What if I just minimize that next order term as my cost function? So of course we want to check if it works. So we can simply just do this and it gives us a pulse for what would minimize this alpha 2 in front of the second order of the adiabatic gauge potential for this Hamiltonian and for the protocol where lambda is driven between 0 and 1. But we want to kind of test it, right? So again, we have to do that some dynamics, of course, numerically, but this is us just doing it once. So we're running the optimization for the pulse over the properties of the adiabatic gauge potential, which takes no time whatsoever, takes up no memory in this problem. And then we're running once some tensor network protocols for the dynamics for our largest chain for 30 sites. And of course, because we're optimizing over the adiabatic gauge potential isn't really relevant for the longer timescales, so it doesn't really do too well here. It'll always do well when you go large enough, just because whatever you do will be adiabatic. But as we start to drive faster, we find that we get quite a good improvement and implementing this down to about 0.9 fidelity. And we can scale up a little bit in system size, and because I picked the n equals 30 to show the plot here, we only have one more in size here, but you know it's obviously scaling in some way because we're optimizing the two body terms, and they're probably becoming less important as we move up. But we still do relatively well even for this 50 size system. Okay, so how do we expand upon that and go beyond so this simple chain example? And I'm going to say that we just from the area, we haven't actually done that. We haven't actually expanded this idea beyond this yet. We're in the process of doing that, but because we got distracted first by trying to come up with efficient ways to numerically calculate the adiabatic gauge potential. And this is the archive paper that just came up today. So we're going to simply take the integral Ising model. So relatively simple. We're again going to drive lambda, and then the complexity of this problem is going to come from the geometry of the graph instead of any property of the Hamiltonian. And then this is, of course, very important, I think, for an important problem for annealing problems, for networks especially, and I think feeds into quite a lot of what people are doing in annealing procedures these days. So of course we can take different graphs, we can consider the physics ones, the ring and the chain and the complete, and then we consider what will be most of the graphs, the properties of most graphs for larger sizes, which will be asymmetric. And the kind of algorithm we've developed to calculate the adiabatic gauge potential, it uses this commutator form of the to find the AGP. And so basically one of the first questions we had was that, yes, of course, goes L equal 1 to infinity, but for any finite system, I'll only have a finite number of operators that the adiabatic gauge potential could have any value on. And then this commutator relation further restricts how many operators I could potentially have a non-zero alpha on, because they have to appear in this commutation relation. So our first kind of consideration was, well, how does that scale? How does the number of operators which could potentially support the adiabatic gauge potential scale? And my hope from starting from this with this sort of form was that hopefully this won't scale exponentially in most problems. And this graph is a little bit deceiving. You would see that there's a lot of things that's in exponential scale. This is the number of potential operators that the adiabatic gauge potential could have support on for all graphs up to a size 8. And you can see here that we have analytical examples for the complete chain and ring, which I'm not really going to get into. And then we have this sort of blob here. But as we go up, we actually find that most of the states actually sit at these points here. So this is the n equals 6, for example. So this is the number of graphs that sit here. And as we go up to 8, you see that the proportion of graphs sitting on this yellow line has increased. And actually, it will forever increase, because that is all of the asymmetric graphs in the problem. And of course, your first asymmetric graph comes up at 6. So this is the first time we see something hit this exponential scaling. And then, we see many, many graphs as we go up. So that's not very, wasn't the result we really wanted, but it's the result. Now, of course, that doesn't mean that the adiabatic gauge potential has a non-zero value for every single one of those operators. But it means that that's like our space that we have to live in to solve our problem, which is not very good, that it's scaling exponentially with the problem. And if we look at the asymmetric graphs, so this is literally looking at this graph here, the n equals 6 site graph with one connection added to the chain, and we solve for the adiabatic gauge potential. So this is the alphas that appear in front of this commutator relation in the problem, up to, I think, maybe the first 100 or so that I think are plotted here. And below here is the norm of the adiabatic gauge potential with said alphas. We just see this sort of like noise pattern. We just have numerical instability, basically. But what's really interesting is if you take this noisy thing and we applied it to, so with if we solve the time-dependent Schrodinger equation for the dynamics, with this being our counter-diabatic driving in a way, then we would get perfect fidelity up to numerical precision pretty much. And it's pretty interesting that would happen. So the adiabatic gauge potential must be hiding behind that somewhere. And of course, if we then take cutoffs in our approach at various places, take thresholds, then we start to find forms that look a little bit more physical for the problem. But of course, this causes a bit of a problem for us, back to this barrier thing. If I wanted to then use this method that we've developed to calculate the adiabatic gauge potential to create cost functions to optimize protocols on asymmetric graphs, then I have a bit of a problem, right? Because I don't know for certain whether I've got this threshold correct at the moment, unless I do some quantum dynamics to confirm that my adiabatic gauge potential gives me unit fidelity if I use it in a counter-diabatic driving protocol. That I have described all diabatic terms that are important. So the big question for next is really, how do we verify that and move that forward? Okay, so I hope that I've convinced you that, well, I don't think anybody needs convinced of this, but I hope that I've convinced you that at Strathclyde we're making efforts towards controlling adiabatic protocols beyond the regime of classical simulability, and that this is not easy to do. that we don't want to solve problems. We don't want to solve the problem in the process. So that means by solving for the adiabatic gauge potential, we don't want to just solve the problem that we initially had, because then we wouldn't be using quantum at all, though that would be a nice quantum-inspired method, I guess. And we don't want to end up with some problem of similar complexity, and the jury's kind of out on that one still. But the adiabatic gauge potential describes all non-adiabatic dynamics, and I think it's a quite a useful thing, especially to do this thing approach that we did on the end of the code paper there of using it as a cost function. And as I said, the next steps, we really want to apply it as a cost function for the Eisengraph problems. We've also kind of got more thoughts on trying to use the adiabatic gauge potential for the using the ground information from the ground state as well, which is a bit more of a targeted approach, but then you'd be stuck at the static barrier that I talked about at the start. Of course, I'm very interested in trying to take this code protocol that we developed with Yeva and applying it to more elaborate settings and using it for different control protocols. We really just did like, we added a single sine term and just optimized the coefficient in front of it, because that did really well for the examples we were looking at. I don't think we proposed that as a way forward. And also the adiabatic gauge potential for sort of general unitaries or gates is something, or this sort of approach to optimizing gates is something that we're quite interested in. Thank you. Hopefully not too over time.
Great, thank you very much, Callum. That's a very nice presentation. A round of applause from me on behalf of everyone here. And I'll now open it up for questions, if Callum's happy to take some questions.
Hello.
Hey,
Can you
hi.
hear me well?
We hear you.
Yeah, so this is something that I only remember vaguely because it's been a while since I read the papers. But my impression was that this adiabatic gauge potential as a function of the position in the protocol, at least for the gapped ground state, it is approximately local. Then there was some result like that. So, and when the gap closes, it stops being local. I'm just wondering why you're not quoting that.
I mean, why am I not quoting that? I mean, I don't think I really came up during the presentation. I mean, I am aware of these results from a while ago, and I think they're correct. I can't remember if there was some assumptions built into them, but if they were, they weren't over the top. I remember that much for sure. But the point is that I want to look at this for problems where we can't do control well, right? If I live in the scenario where I have a big gap all the time, well, adiabatic does good for me, then I don't need to really worry about applying control protocols or optimal control to the problem too much. Or I maybe do a little bit for when we're scaling up system size, but I would say where our interest really lies is at that point, at the point where you're closing gaps and where you're going through things that are, so either that is you're going through a transition point, or you're going through some local transition point in the sense of your spectrum. That is probably where we're more interested in utilizing this method. Now, I'm also happy to use the local terms. I don't have a problem with that. And it is true, I think, that all the results that I am aware of, if we have a large gap, they're consistent with the fact that if you have a large gap, then your AGP, your adiabatic gauge potential, will be relatively local.
Yeah, so I guess I was surprised that in your pictures, it seems that you don't get convergence at most of the time during the anneal, even for small graphs, even though the gap for the 6-side graph probably closes only like a couple of times during the anneal. So I would expect you get convergence
but these are
everywhere.
asymmetric graphs. So this is where where local is now, because local there, I think what you're meaning when you say local in that problem is local with respect to the Hamiltonian. Now that Hamiltonian
Right.
for the asymmetric graph is not very local anymore. So the AGP will be local with respect to the Hamiltonian, but it will involve connections further in distance because the Hamiltonian has connections further in distance. And I think it's them that generate a lot of the problem. And actually, a lot of the problem for the asymmetric is entirely that you just have a lot of terms that can potentially contribute to your AGP. Now, I think I'd be interested. I haven't actually, I think in your point is very good in the sense that I haven't revisited those papers in a while. So I should dig them out again. because I think I know the ones that you're on about, because I'm all for it, anything that could help us reduce the potential space that we need to solve. So the paper that we put out there was really like, let's go absolutely crazy and say we want it exactly in every scenario. How well can we do? Of course, we're all realists probably here, right? We understand that you probably don't need it exactly in every single scenario. There's places where, approximations could be very valid. And so that might be something worth revisiting.
Yeah, so the graph you had as an example was low degree, which is essentially the same as local. So I would expect that you get good convergence anywhere except the avoided crossing, and you should actually have like low or like no these instabilities or anything you see.
So you're kind of correct, but the instabilities are definitely there. But I think what I would say is that it's because for this problem, this one connection actually plays quite a big role. Now, if I extended this out, so if I extended these two chains out like this to a bigger graph, that graph is still technically asymmetric. But in that problem now, this connection here becomes more like a defect and more like kind of what you're saying, and it doesn't play too much of a role. And there we can do quite well by basically approximating the problem to be that of the chain with a small defect from the asymmetric. And I think that feeds into perhaps what you're talking about here. I'd be very interested in revisiting that again. But for the asymmetric graph again, because it's all relative to the one that you pick for this 6-side graph, which is a small problem, this one connection actually plays a very large role. It's not just a small part of the problem. And it's entirely because we're trying to solve for the adiabatic gauge potential exactly from the start. We're not building it up in a way like by going from local terms and then seeing some convergence, which would probably do better in this scenario. We're really trying to say, I want a method that will numerically give me the exact adiabatic gauge potential immediately, not through this convergence of parameters. And that's because we wanted to apply it to more complex settings.
I see, thanks.
But I think both ways are very valid and both ways are very useful.
Are there any other questions for Callum? If not, let's thank Callum once again. Thank you, Callum. And look forward to seeing you at next week's online seminar. Thank you very much. Bye-bye, everyone.
Bye. Thanks. Bye.